guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So students often hate talking about significant figures, but this is a really important concept and it takes a lot of practice for you to get used to them, but you're going to use it for the rest of the quarter throughout your whole course, so make sure you understand it really well. So to start off, a little comment on significant figures. Basically, no measurements are completely exact, and so it's really important to state experimental results with a number of significant digits, which gives a reasonable impression of the accuracy of the measurement. For example, if I had a rock, let's say it looks like this. So the mass of the rock was measured to be 8.2 grams, and its volume was measured to be 2.3 centimeters cubed. From knowing these two values, how accurately can I determine its density? Okay, well, we know that density is mass over volume, right? So the mass is 8.2 grams, and the volume is 2.3 centimeters cubed. So right now, I can tell you that this is measured to two significant figures, 8 and 2. This is also measured to two significant figures, 2 and 3. When you plug this into your calculator, you're going to get a number that's like 3.56521739, etc. Can you write this as your answer for the problem? Well, no, because all of these points that keep going on is a value that you're not certain of. So let's put the units first, grams per centimeter cubed. And so basically, you need to round this number in order to use the right number of significant figures. So this actually makes it 3.57 because we rounded up this 6. Because this is 5, but I'll talk about that in a little more detail in a second. So basically, it's reasonable to carry an extra digit or two in intermediate calculations. But ultimately, after rounding, the best answer for this problem is 3.6 grams per centimeters cubed. It's better to keep only the number of digits of your weakest measurements for your final answer. So in this case, we started out with two significant figures, both the numerator and the denominator, so your final answer should also have two significant figures. And this is the best estimate of the density I can give given these two values. On the other hand, if someone had said it's 8.201 grams over 2.357 centimeters cubed, then in that case, my answer could have been 3.565. And since this is a 2, I would not round up, I would round down. So in this case, I could have 4 significant figures because I have 1, 2, 3, 4 on the top, 1, 2, 3, 4 on the bottom. So now let's get more into the nitty-gritty of sig figs. So like I mentioned previously, if we have a number, let's say 50.00 grams, we can rewrite this as 5.000 times 10 grams, right? That's just multiplying 5 times 10 to get 50. This has 4 significant figures. On the other hand, if you have 0.00501 meters, we can rewrite this as 5.01 times 10 to the power of negative 3 meters. And thus, this has 3 significant figures. Another example is if you have 22.0 milliliters, this has 3 significant figures. But if I had 0.22 grams, this has 2 significant figures. So are you seeing a pattern here? Basically, the zeros that come after the decimal point count as significant figures. That's why this one has 4 sig figs. In this case too, there's a 0 after the decimal place. So thus this has 3 significant figures. But when there's zeros in front of the actual numbers, so here we have 1, 2, 3 zeros, but the only thing we count is the 501, that has 3 sig figs. So basically the zeros that come before the actual numbers are not counted. So in this case, we have one guy right here, but the actual number of sig figs is 2. So that's one basic rule. Another thing is when you add or subtract. And you have to pay attention to this because adding and subtracting is different from multiplication and division. So the number of decimal places in the answer is equal to the smallest number of decimal places, which I'm just going to write as dp, in the data. So what does that mean? Let's do an example. If I have 1,000.1 grams plus 7.34 grams, this equals 1,007.44 grams. Now let's look at this. We have how many sig figs here? We have 1, 2, 3, 4, 5 sig figs here. And we have 1, 2, 3 sig figs right here. So how many sig figs should we end up with? Well, since this is an addition, we just need to care about the number of decimal places. So this has 1 decimal place, dp, and this has 2 decimal places. But all we care about is the smallest number of decimal places in the data, which is this guy. And so your final answer is just going to be 1,007.4 grams because we're rounding to 1 decimal place. So on the other hand, now we can talk about multiplying and dividing. So in this case, you just use the lowest number of significant figures. So lowest, let me underline this, lowest number of significant figures that's carried over. For example, 1,007.44 grams that we just got divided by 1.23 moles. This gives you 819.0569 grams per mole. And you'll find out later that this is a unit of molar mass. But we'll talk more about moles later. Okay, so let's look at how many significant figures all of these things have. We have 1, 2, 3, 4, 5, 6 sig figs for the numerator, and we have 3 sig figs for the denominator. So the lowest number of significant figures is 3. So we can only write this as 819 grams per mole. So I hope that makes sense so far. If it's adding and subtracting, use the smallest number of decimal places. For multiplication and division, use the lowest number of significant figures. It's as simple as that. You just need to get used to doing some problems.